happy to be finally here. Sorry for the delay. I had another appointment. So my presentation today is on a new approach for measuring blooming of LCDs and OLEDs. Such a special topic of modern high-end displays and how to compare them. We invented a new method how to measure halo or blooming on a so-called pixel-based level, and that's what I'm going to present right now. First of all, I didn't this slide on. Just a second. There's something going stuck. Let me do it that way. Okay. Here are a few words about myself. I'm full professor at Pforzheim University, founded and head as a display lab of our university some time ago, and I'm a member of the major networks and organizations dealing with displays and LEDs. At our display lab, we do not do really displays. Displays is a component for us. We measure, for instance, the optical output to the data interface, build in terms of prototyping complete system with displays, touch, gesture control, image processing software, etc. This slide shall provide you an overview of my presentation. After an introduction, I introduce you to the measurement method, followed by the results of our measurements, and last but not least, the evaluation of subjects. On the right side, you see the motivation for our work. As you might know, Germany is the country of premium and high-end cars. Means in those cars, highest visual quality is expected, but this is as well not only true for cars, but as well in the AV or movie industry, for instance. So let's start with the introduction. The slide on the slide on top right in the center, you see an example of what we call blooming or halo. There's a tiny pencil on the screen in white, and this pencil, and I'm sure you can see it, is surrounded and by, let's say, brightened areas. And these brightened areas are non-uniform, and this is also a hint that this is first an LCD with local dimming backlight, because those irregularities of the blooming corresponds to the pixel pitch of the so-called local dimming LCD. I'm going to present this more in detail. This blooming is very disturbing for the observer and is also a serious issue for medical X-ray imaging, for instance. If you Google for blooming or halo, you will find a lot of pictures, a lot of impacts and websites on all social media and the internet. However, we have to state that this blooming is always exaggerated, means you set your screen to full luminance or full brightness, being a dark room, and capture pictures. That's not typical. Under normal conditions for well-made LCD or OLED, blooming is hardly to perceive, but except for night drive, medical imaging, and movie industry, this halo is essential to be quantified and to be measured, and that's our talk. There are other methods already proposed how you can measure image quality with white content surrounded by black and vice versa. For instance, starfield contrast, corner box contrast, or signal black means in the center. Here we see a black image. Data black means gray level 0. This is surrounded by bright area, and now you measure the luminance of the spot, and you might notice or measure that this black luminance is higher compared to the case that the full screen shows black. You can capture as well the influence of viewing glare of your instrument, of your imaging instrument with optics, with lenses, and vision suffers as well of so-called viewing glare. A measurement procedure which is somewhat close to our method is a so-called halation method, where you measure the luminance of the black area surrounded by white, depending on the size, the area ratio of black to white. However, these are just first measurements, but doesn't help to solve the issue of blooming. Here we see the comparison of the impact of blooming or halo for standard LCD on the left, a local dimming LCD in the center, and an OLED display on the right. The drawback of a standard LCD is that you have light leakage due to the limited contrast ratio. So an improvement to avoid this light leakage is a so-called local dimming or full array. Local dimming backlight, you have a high resolution LCD in front, and the backlight is formed by several thousand, hundreds to thousands LEDs, and they form a blurred image. You have a diffuser on top, so only areas where the image is bright are lit by the backlight. This offers, beside higher luminance quality, because you have no light leakage here at the edges, as well as significant reduction in power consumption. Last but not least, OLEDs have true black. Nevertheless, tiny white areas surrounded by black might suffer of halo or blooming as well. And that was the main motivation for our partner who granted us this research from a major OLED manufacturer to investigate that. So let's come to the measurement method. As I already said, we measure bright areas here on the left, and to avoid measurement errors by light leakage into the lens system, etc., you have to block this, but what you see here is the halo of an OLED. So let's start with some basics. For the OLED, we have an emission layer. Only there light comes out. However, the so-called waveguide or total internal reflection affects light spreads in neighboring, let's say, black areas, and this is a range of 0.02%. In the next step, we have a look to a standard LCD. We have this effect as well, but it's not visible because of the light leakage due to the limited contrast ratio. For fault LCDs, we have to differentiate between low resolution fault, means there's a certain distance between the backlight LEDs. So you have some light leakage as well, or so-called high resolution fault display. We have a weak diffuser to make the LED backlight more uniform, but you will see as well some halo. So now let's start with our 5-step method. The basic setup is we use an imaging luminance measurement device. That's a calibrated camera for luminance and color. We have a display under test. We measure perpendicular in the center. So basically, we investigate on so-called profiles we can get out from the software of this measurement device and instrument systems. So one method is called A. You measure first the luminance of the emission, and in method B, you measure the whole profile of the on pixels and the neighboring pixels. Means this profile on the right side, it's the sum of both blooming and halo and lens glare. In the second step, a black mask comes in to get rid of the lens glare effect. Method A, we now block the emitting pixels, the bright pixels, by a black mask, and so we are able to measure directly halo. For method B, where we have already captured the profile of on-pixels, lens glare plus halo, we cover the halo area by a black mask, and therefore we just measure the lens glare. And the lens glare, the amount depends on the quality of your lens. So in the next step or section, I show you the results of the further steps. First, we started to verify that we are really measuring halo. The assumption is, and we proved this as well, that the halo to the waveguide principle depends on the luminance of the pixel. And the easiest thing to adjust this is using different gray levels that you see on the right. And if we normalize then the measured halo luminance profile divided by the luminance of the display of the on pixels, you see that this curve is independent from OLED of the gray levels. So this makes sure that we are really able to measure halo. On fault LCD, it looks a little bit different. The curves here are the same of the halo measurements. However, the normalization shows that it's not the same result. Means for this halo LCD, the percentage or halo divided by a display is not independent. And this needs further study as well. And for the further study, we moved to a small line, which we extended in the lens and measure the luminance of this line and the halo here on the right side. For the OLED, we see that the luminance of this line of variable length is constant. And the halo amount here in blue, in percentage, scale is on the right, increases. That's what you're gonna expect. The more pixels you have, the more halo you get. But due to the decay of the waveguide principle, at a certain amount, making the line longer doesn't affect the halo outside the area measured here, where the blue, yellow spot is. Opposite to that, for the fault LCD, the luminance of these tiny lines increases until the line length was in the range of 50 pixels. And 50 pixels around is the width of a so-called local dimming zone. Means if the object is smaller than the local dimming zone, the luminance is reduced. That's not good for readability in cars, for instance. And if the size of the object, in our case, the line becomes larger, it's independent. And we see as well that the halo here in blue is independent of the line of the length. This is as well a hint that halo is more serious on fault LCDs than on OLEDs. So in the next step, we compared method A and method B. Method A, you remember, we measure the halo directly by a blocking mask, and method B was indirect method. We measure halo, lens glare, and subtract lens glare in the second step. This is shown on the four charts on bottom. First is a measurement, and this modulation comes here from the pixels. So we measure really a pixel resolution. If we smoothen that by a moving average filter, we get for the fault LCD 60K. And then we subject the measured lens glare of step 2, and this is our result. And we compare this now to method B, and you see it's roughly the same. So you might argue method B is quicker and easier, that's right. However, method A needs some more effort, but less explanation as you measure directly halo and not indirect like in method B. So using these results from high magnification measurements, you see here the OLED pixels. We have the luminance profile, and then we make a simulation with single pixels. You see it here, and have the exponential decay, as you see here as well on the right side, and modify the parameters of the exponential decay until the measured profile is achieved. And this is very easy and simple to do, and therefore we have proven that we are able to measure single pixel. So that was a measurement method. However, we wanted to know if we could really measure, evaluate this halo by subjects as well. Why is it important? First of all, for the traditional negative mode GUI, what we have in cars today, and there are some design studies of automotive and car manufacturers to have a favorable so-called positive mode like halo. What is the effect? The effect of blooming and halo is that surrounding areas get brighter. This is here where the backlight LED is directly behind the icon, but as the icon can be placed everywhere randomly, it could also be set surrounding areas only. And for positive mode, all bright light from the surroundings spreads as blooming or halo into this tiny black symbol. So on this basis, we make evaluations with subjects. However, due to COVID, just 8, but 6 of them were display experts. And at the first test in the negative mode, we use this, what I showed you, forced luminance halo method, and the subjects had to judge where they do halo, and with a measured luminance and gray level, we are able to say that for reasonable distance in darkroom, here you see it's done in darkroom, 16 cameras per square meter is typical, so you can see 1%. However, 1% is in the same range as the viewing glare of your eyeball. And the more you increase, the percentage drops means this is, for instance, daylight condition here, 364 cameras per square meter, and therefore halo is perceived more severe. Compared to bright light conditions, halo must be at least an order of magnitude higher than forced halo before it becomes noticeable by the machine. We did the same by a select test to judge on the threshold, and the threshold in the select test was around about 10% of the display white luminance, nearly independent of the surrounding. And with that and the random test, we were able as well to extract the threshold when halo is or blooming is noticeable or hardly noticeable. For negative mode, it's in the range of 1%, and for positive mode, it's in the range of 10%. So this brings me to the summary. So blooming or halo is an unwanted spread of light into dark areas. And this picture from the internet references on the first page is as well an effect of halo of moonlight unit. This blooming occurs for all display technologies. However, LCDs are more effective than OLEDs. There have been some measurement methods proposed, but they are not suitable for single halo or halo or blooming measurements for characters or other icons. He invented a so-called 5-step method, including a macro lens for a single pixel halo. And what we observe from a high-end local dimming LCD versus a high-end automotive OLED, the halo is an order of magnitude larger for a state-of-the-art LCD compared to OLED. The evaluation shows that the threshold is about 1% of the white luminance. The light luminance as well generates eye viewing glare. However, we have to state that positive mode is less affected. What our next goals are is to standardize with partners from the automotive industry and the AV industry this kind of measurements standardization, because then the quality of the display, for instance, also for medical imaging, can be better evaluated. So extremely low halo in consequence is essential for viewing displays. Thanks a lot for your kind attention.
Thank you so much for your presentation. Floor is open for the questions. If anyone having the questions.
If not, please feel to contact me via email.